Howdy! Welcome to Elementary Statistics. I am Lance Curtis, and this is the lecture for Section 4-3, Complements, Conditional Probability, and Bayes' Theorem. In this lecture, we're going to look at how to calculate the probability of at least one. We'll look at what's called conditional probability, which is the probability of one event given that another event occurs. We'll look at what statisticians call confusion of the inverse, and then we'll touch briefly on Bayes' theorem there at the end. So let's get started. Here in this lecture, we're going to learn how to calculate the probability of at least one, which is the probability that among several trials we get at least one of some specified event. And as I mentioned, we'll also look at conditional probability, which is the probability of an event when we have additional information that some other event has already occurred. Let's start by looking at the probability of at least one. So in a problem statement about probability, when you see the words at least one, you need to think that this means one or more, because those two phrases are equivalent. Now if we take the complement of getting at least one item, then that means we're going to get no items of that type. And if you think about it, this should make sense. What exactly does getting at least one item mean? Well, if we have one item, then we have at least one. But we also have at least one if we have two items, or three items, or four items, or five items, and on it goes, all the way out to infinity. So the complement of getting at least one is everything that's not within that area of at least one. And the only number that would be within, not within that area is zero. There's no such thing as a negative number of items. So we're not looking at negative numbers. And all the positive numbers, one from on, they're actually part of at least one. So therefore, the complement of at least one is zero or nothing. And this makes the calculation for the probability of at least one very simple if we use this principle of the complement. All we have to do is take one, subtract out the complement, and then we get the probability of what we're looking for. So the probability of at least one is 1 minus the probability of none. Let's look at an example to illustrate. Topford supplies X data DVDs in lots of 50. They have a reported defect rate of 0.5%. So this means that the probability of a disk being defective is 0.005. If this is the failure rate, 0.005, then it stands to reason that the success rate, or the probability of a disk being good, is 0.995. The question we're asked then is, what is the probability of getting at least one defective disk in a lot of 50? Well, by what we just learned, the probability of at least one is 1 minus the probability of none. In this case, the probability of at least one defective disk in a lot of 50 is the same as 1 minus the probability of no defects in all 50 disks. You may be wondering at this point, okay, that's great, but how do we calculate the probability of no defects in all 50 disks? Well, think about what that means. The probability of no defects in all 50 disks is the probability that the first disk is not defective, and the second disk is not defective, and the third disk is not defective, so on and so forth until we get to the 50th disk. Well, that word "and," as we know from the previous lecture, signals multiplication. So we're going to take the probability that there are no defects in the first disk, multiply it by itself 50 times. So that's what we do. The probability that there's no defect in the disk is 0.995. And so it is for all the 50 disks. So we're taking this number and multiplying it by itself 50 times. We then take that number and subtract from 1, and that gives us the probability of at least one defective disk in 50. So we punch this out. on our calculator and we find that 0.995 raised to the 50th power is 0.778. We then subtract that from 1 and get 0.222. So the probability that at least one defective disk is in a lot of 50 disks is 22.2%, which from a manufacturer's point of view probably seems pretty high. You want to take a look at your manufacturing process and see what is it that you need to change in order to lower that probability. Now, you wouldn't think that you'd get something like that. After all, the reported defect rate is only 0.5%, and 0.5% as a failure rate sounds great, but look at the math. Obviously, there's a problem here that we're going to get at least one defective disk in a lot of 50. So for approximately every 5 lots that get shipped out, there's going to be one that has defects in it. That's probably not great for business. So if I were in Topsford's shoes, I'd be looking at the manufacturing process and seeing what can we do to reduce that probability. Let's talk now about conditional probability. Conditional probabilities are pretty common, and so it's important to know how to calculate them. First, let's talk about the denotation. You see here P and then B, and then there's a line, and then there's an A, and all that's in parentheses. So the probability of B given A is how we would read this. What this is denoting is that there's an event A that has already occurred, and we want to know what's the probability of B given that that first event A has already occurred. The way we calculate this is by dividing the probabilities of event A and B, both occurring, by the probability of event A. In mathematical terms, this is how we would calculate it. So the probability of B given A is the probability that both A and B occur divided by the probability of A. This calculation is usually fairly simple if you're looking at the data for your sample in a tabular form. So if you have a table of the data, it's usually really easy to calculate conditional probability. Let's take a look at an example to illustrate. What is the probability that a subject testing positive actually uses drugs? So here we have our data for our sample here in tabular form. So we see that there's 44 people who test positive and use drugs, 6 people who test negative and use drugs, 90 people who test positive but don't use drugs, and 860 people who test negative and don't use drugs. We get our sample space first, so we add up all the numbers there in our table to get the total, and we find that there are 1,000 total subjects. So this is our sample space. Next, we're going to use our formula for conditional probability. So the probability that a subject testing positive actually uses drugs is the probability that a subject uses drugs given that that subject test is positive. This is equal to the probability that a subject uses and tests positive, so both events occurring together, divided by the probability that the subject tests positive. Notice the relationship here between the different events. So we have on top of our fraction the probability of both of these events occurring together. But here on the bottom we have just the probability of the one event here at the end of our conditional probability statement. So the probability that the subject uses, given that the subject tests positive, that positive test is going to be down here on the bottom of our fraction. Now we get to put numbers with what we have here for our probabilities. So to start out with, let's see what this equals to. The probability that the subject uses and tests positive will be 44 over 1,000. We know this is so because the 44 comes from the part on our chart here, our data table, that is both positive and uses drugs. So this number is going to go here, divided by the total, which is the 1,000. That's our sample space. That gives us the probability the subject uses and tests positive. the probability that the subject tests positive is going to be 134 over 1,000. The 134 comes by adding the numbers there in the column for the positive result. So we have 44 plus 90, which gives us 134, divided by our sample space of 1,000, gives us the probability the subject tests positive. Now we've got our numbers. Let's go ahead and punch this out on our calculator. The thousands will cancel each other out, leaving us 44 over 134, and we divide that out and we get 0.328. This then is the probability that a subject testing positive actually uses drugs, which, looking on the face of it, that doesn't seem like a very effective test. I mean, if you're testing positive, there's only a 1 in 3 chance that you're actually using. That doesn't sound like a very effective test to me, and I'd hate to be the subject of that test because it's more probable that if you get test positive, that it would be concluded that you don't use drugs, and that could lead to some unfortunate consequences. Let's talk for a moment about confusion of the inverse. And when I get to this topic, I have to do a Jackie Chan, put my hands up over my head and get this really contorted look on my face as if I'm saying, "What in the world are you talking about?" Because this is a phenomenon that statisticians have actually identified and labeled as though it's something separate. Basically, they're defining it as the incorrect belief that the probability of A given B is the same as the probability of B given A, that these values can be used interchangeably. This is what they call confusion of the inverse. Generally speaking, the order of the elements in your conditional probability matter. It does make a difference. Now, there are instances where it doesn't, but most of the time it actually does. So, to actually label this as a typical phenomena that people are experiencing, to me seems ridiculous. I look at this and I want to do a Jackie Chan. What in the world are you talking about? But when the statisticians talk about confusion of the inverse, understand they're referring to the order of the elements in the conditional probability. The order actually matters. Generally speaking, the probability of A given B is not the same animal as the probability of B given A. Now, as I said before, sometimes they are. For example, let's say we have a mother who's giving birth to 2 children. So event A is giving birth to a girl, and event B is giving birth to a boy. In this instance, the probability of having a boy, given that you already have a girl, is the same as the probability of getting a girl, assuming you already have a boy. Because the probability of having either a girl or a boy is roughly the same, and births are independent events. So having a boy or a girl does not depend on the birth of any previous child. And the probability of getting either one is about the same. So in this instance, the conditional probabilities are the same regardless of how you order the events. However, this is rarely the case. Usually what happens is that these probabilities are not the same. For example, suppose that A is the event of it being midnight, and event B means that it's dark outside. Well, the probability of B given A says that it will be dark outside given that it is midnight. And that's very likely true. I mean, when it is midnight, it's usually dark outside. However, the probability of A given B says that it will be midnight when it is dark outside. For the most part, except for like 1 minute of the night, that is not the case. So we see here an instance, and this is more often the case, the probability of A given B is not the same as the probability of B given A. So you want to make sure that you distinguish between the order of your elements because it actually matters what it is that you're looking at. You cannot use them interchangeably. Incorrectly assuming the order of conditional probabilities doesn't matter is what the statisticians call confusion of the inverse. Your author then uses this as a segue into Bayes' theorem, which is also called Bayes' rule. We use Bayes' theorem with sequential events. And essentially we're using it when new information about a subsequent event prompts us to recalculate the probability of a previous event. So we must therefore distinguish between what's called prior probability and posterior probability. A prior probability is the original probability value before obtaining any new information. A posterior probability is the revised probability value in light of obtaining new information. So typically, we'll calculate a probability, and this will be a prior probability. Then new information comes to light, suggesting that we need to adjust the probability that we counted prior. So we recalculate it, and that revised value now becomes a posterior probability. It is the prior probability that has been recalculated due to new information that has come to light. Mathematically speaking, Bayes' theorem is usually expressed as the probability of A given B is equal to the probability of B given A times the probability of A divided by the probability of B. I know this equation looks very different from the one your author presents in the textbook, but keep in mind that the author presents in the textbook, according to his own claim, a formula that often comes with Bayes' theorem. But it is not actually Bayes' theorem. It is just something that is used along with Bayes' theorem. Bayes' theorem is what you see here on the screen. It's much more simple. I'm not sure why your textbook author was trying to present something more complicated, especially since he doesn't really use Bayes' theorem all that much in the particular section here. But be that as it may, this is how you express it mathematically. Let's take a look at an example to illustrate how this would be used. So there's a study of the response physicians give to patients regarding a cancer diagnosis. In this study, about 95% of physicians were overestimating the probability that a patient has cancer given a positive test result, and they were overestimating it by a factor of about 10. The table here on the lower right-hand side of the screen contains results for 1,000 patients based on that study. So here we see that we've got 8 subjects who tested positive for cancer and actually do have cancer, 2 subjects who do not test positive for cancer but actually do have cancer, 99 subjects who test positive for cancer but don't have it, and then 891 people who test negative for cancer and have no cancer. What then is the probability that a patient actually has cancer? We know how to solve this. Take the part and divide by the whole. The part are the patients who actually have cancer. So this will be the 8 plus the 2 from our table here. These are the people who actually have cancer in the sample. The whole is in the sum of all the people together. So we take all of them together and we get 1,000, which we should, because we were told this was results for 1,000 patients. 8 and 2 is 10. 10 divided by 1,000 is then 0.01, or 1%. Therefore, there is a 1% probability that a patient actually has cancer. Let's put in the test result then. Let's say, what is the probability that a patient has cancer given that patient tests positive? Well, we know what this is. The probability that a patient has cancer given a positive test result is the probability that the patient has cancer and a positive test result divided by the probability of a positive test result. This then converts into our numbers, which we get from our table. So the probability of having cancer and a positive test result is the 8 we see right here, divided by 1,000. Positive test result would be 8 plus 99. That's the positive test column here. So now we're dividing by 1,000 each here, so we cancel those out, get 8 over 107, divide that out, and we get 0.075. This is the probability that a patient has cancer given a positive test result, which doesn't seem all that promising. I mean, think about it. You get a positive test result, but there's only a 7.5% chance that you actually have cancer. Wow, that's really good news, actually. It is something that should be communicated to the patient when the doctor says you may have cancer. Of course, the study was finding that 95% of physicians were overestimating that probability. They were actually confusing the one with the other. So let's look at part of the confusion when you switch the order of the elements in the conditional probability. What is the probability that a patient has a positive test result given that he or she has cancer? So here we have our calculation again. Probability that the patient has both cancer and a positive test result, but now we're dividing by the probability that the patient has cancer. Again, the order of the elements makes a difference. And we see that's true when the numbers come out. So we have 8 over 1,000 on the top, just like we did previously, but now the probability that a patient has cancer is going to be the 8 plus the 2, which is 10, over 1,000. This then leads us to canceling out the thousands because there's the same on both top and bottom. That gives us 8 over 10, which when you divide out is 80%. So you can see that clearly having cancer and having a positive test result are not interchangeable. The order of the elements matters when you're conducting a conditional probability. There's something else at work here, though. Looking at the distinction that we make in Bayes' theorem between a prior probability and a posterior probability, in this example, the 1% would be considered a prior probability. It is the probability that a patient actually has cancer, which is 1%. However, the probability that a patient has cancer given a positive test result would be an example of a posterior probability. So the positive test result gives us information that we didn't have before when we calculated the prior probability. So we recalculate our probability, including the new information, and we come out with a different value. This is part of what Bayes' theorem is all about. But this is also as far as a textbook author goes with using Bayes' theorem. So again, I don't know why he's including this in this particular section, because he's not really using it all that much, but there you have it. So the 1% is a prior probability. We conduct the test, we get a positive result that gives us new information, and so we revise our probability. So when the doctor is giving the patient a diagnosis of cancer, the doctor shouldn't be saying you have cancer and causing a lot of unnecessary turmoil. I mean, yes, there's an 80% chance that your patient has cancer given a positive test result. Excuse me, that your patient that a patient that has cancer gives a positive test result. But just because you have a positive test result, with that alone, there's only a almost 8% chance that the patient actually does have cancer. So this information needs to be communicated to the patient, saying, look, there's only a 1% chance that any one person has cancer, and this positive test result that we got back from you simply raises that probability from 1% to 7.5%. There's still a really good chance that you don't have cancer, given the positive test result. This speaks volumes about the test itself, but it also says about how the doctor should be communicating the information to the patient to avoid any sort of unnecessary emotional turmoil. If the doctor would present these numbers in this way, then there would be a lot more hope communicated. Now, there may be that, 7.5% chance that it's actually true. And in that case, there are treatment options that are available, and many people have been able to beat cancer with those treatment options. So even in that instance, it's not all said and done. But you can see here if you actually sit down and do the math and do the numbers, you actually have cause to give more hope and consolation than you do the opposite. That brings us to the end of this lecture. If you have any questions, you know what to do. Otherwise, I will see you in the next video. Thanks for watching.